Thank you. And I thank Marco and all the organizers and John for creating this event, for inviting me to speak.
I didn't create this event.
You did.
Sort of. My parents created this.
Okay, I thank John's parents for creating this event as well. Yeah. So I met John in a faraway September of 2000 and John was one of my very first impressions of Canada and of the world outside of my home city. And so I arrived as a student and then at Concordia, and I saw this famous math professor, John Harnett, who seemingly knew everything and I knew nothing at all. And he was still very nice to me all the time. Every time we interacted, and I still feel like this. So it's a great honor for me to speak at this conference. I'll try to surprise John now a little bit. Maybe not, maybe I won't. But you of course don't remember it, but in 2003, we were in Cadiz for a conference in Spain, in Cadiz. It was my first ever conference, and at the dinner, you taught me to say, I don't speak Hungarian.
In Hungarian.
In Hungarian, yes. And I still remember it. I never checked it with anybody else since. I could have, but I didn't. Right, yes. So maybe I still remember it, but maybe I don't remember it correctly. So I'll try now. Yeah. I think it was Nem beszélek magyarul. Really?
Actually, it's my hovercraft is double parked, but
you see, John is a very good teacher. I just wish I learned more than this, but well, anyway. So I'll talk to you today about a modification of the Schlesinger system that Vladimir Dragovich, my co-author, and I were led to introduce. So it's a joint work with Vladimir Dragovich from University of Texas at Dallas. And this, we came to this modification of Schlesinger system through the generalized Chebyshev polynomials. Okay, so this is a classical Schlesinger system, right? So it starts with the Fuchsian system, where the matrix A has simple poles at uj. Uj are complex numbers. So U is in the complex plane, and uj are some points of the complex plane, the Fuchsian singularities of this system. There is also a pole at infinity, and the residue matrix at infinity is given here. So aj are the residue matrices, and they depend on uj. And now we want to find such systems that are isomonodromic, so that the monodromy of the solution are constant with respect to small variations of the positions of Fuchsian singularities. And right, so with some assumptions, the isomonodromy is one of them. We can also obtain this equation for the function phi. And then the Schlesinger system is a compatibility condition of these two equations, and the solutions of the Schlesinger system give the matrices AJ, which define an isomonodromic system, this linear system. It will be isomonodromic if AJs are solutions of the Schlesinger system. Right. So now what we propose to do is to consider this set of Fuchsian singularities and split it into three parts. The first part is constant. We just put two singularities at 0, 1 at infinity. One of them is already at infinity. And the remaining remaining positions of Fuchsian singularities we split in two sets. Well, in general, in an arbitrary way, but non-empty sets. One set we call xj, and the other set we call uj, and the xj are the independent variables. Yeah, before they were all independent variables, but now we say that, okay, the xj will keep being independent variables, but the uj will be functions of the xj. Yeah? And then we do the same thing, right? We ask when such a system is isomonodromic, and we write the Schlesinger system that comes out of this condition, right? So our Fuchsian system becomes this. There is no change except for notation. The AK matrix, I will now, so instead of labeling it with an index K, I will label it with the position of the singularity. Right? But the second equation is now modified, right? So when we differentiate with respect to xi, we also have to differentiate with respect to all the u's and then use like chain rule, nothing more complicated, right? So now if you compute the compatibility condition of these two equations, we obtain the Schlesinger system, which we call a constrained Schlesinger system because the UJs are constrained to be functions of xj. Right? So the constrained Schlesinger system is here. Right? So the AJ here stands for any singularity. Here, for the first line, this AJ is independent of xi, right? So it's not the xi itself. It's not one of the u's. Here, it's one of the u's, and here we have the same. So if we forget the derivatives, this different derivatives of UK, so if we set them to 0, if we suppose that uj don't depend on xj, so all these terms will disappear and we'll recover the classical Schlesinger system, right? So there are two ways of looking at this system. We can say that a solution of the system is a collection of the functions axi, aj rather, yeah, the collection of matrices A of residue matrices and the functions u of xj, right? But this way the system is very determined, right? We don't have equations for the u's, but we can also say, okay, the u's are given as functions of x, and then can we find the a's, and then we have enough equations, right? Okay. So in what follows, I will show you one solution of such a system that goes through the Chebyshev polynomials. But
Could I just ask you a quick question?
Sure.
Why don't you just forget the constraints, take any solution whatsoever to the full Schlesinger equation, and then restrict yourself to the constraints somehow? That was
And will that be
satisfying.
a good question? I don't know. Will it? Because then you will have the UJs. Well, you'll have A's that depend on U according to this, right?
Yeah, it's just a restriction of a bigger parameter family where you constrained it to a smaller parameter family.
Maybe.
With the chain rule, with the chain rule,
It will preserve the number.
Yes, because
It's preserved, that's all you need. And the constraints are preserved. That's it.
right, maybe.
Maybe we can
Could be.
this
Well,
yeah, into some other part. Yeah.
no, it's an interesting question. I'm trying to find I'm trying to find the
I'm not saying
justification.
that's equivalent, I'm just saying that every solution to the system is a special case of the solution to the bigger system.
It could be true, right? And well, the only problem is we won't be able to go in the other direction, right?
Yeah.
If you have a solution to this constrained one, it will not generate as a solution to the full one, to the non-constrained one.
Missing information. You could
Right.
reduce the number of parameters, you're getting.
Right. I cannot increase it. Right. So that justifies looking at this system, right?
Good.
Because we can go one way, but not the other, right? Good. So makes sense then to look at this system. Okay. So I want to show one solution which does not, and I think we'll see why it does not generate a solution to the non-constrained system. So I want to show this one solution, but I'll start from far away. Here is an elliptic curve, right? And it's Jacobian. Let's just take a point in the Jacobian, just any point in the Jacobian. Right, so elliptic curve is ramified at points 0, 1, x, and infinity. Right? Now I take any point in the Jacobian, I can write it in this way with respect to the lattice vectors to W1 and to W2. C1 and C2 are some constants. And now I'm going to consider a family of such elliptic curves parameterized by the value of x. Right? So when I move x, everything here becomes a function of x. The Jacobian moves, right? It also the w's become functions of x. And now I need to define the z0 on this varying Jacobian. So I define my z0 in the moving Jacobian by this condition, by requiring C1 and C2 to stay constant. So W1 and W2 depend on x, but I require C1 and C2 stay constant. Right? So now I map this point Z0 to here by the Weierstrass function, and then I obtain the point Y0. Right? And this is a Picard solution to Pan-Levy-6 equation with these parameters. Right? Okay, and then I can take a point Q0 on my elliptic curve, which is mapped by the Abel map to the point Z0. So this is a very special case when the curve, my elliptic curve is isomorphic to the Jacobian. So the Abel map is well, the Abel map and the Weierstrass P function are inverse one to each other and one to one another, and the Abel map is a bijection here. Right, so I can have the point Q0 that is mapped to Z0, and then the other way is done by the Weierstrass function. Okay, so I take this point Q0, and I take its elliptic involution, and I create a differential of a third kind with poles here and there, simple poles here and there, residues +1, -1, and then well, this is a normalized differential with those properties, normalized by the A cycle. So its A cycles vanish, but then I add this thing to make A cycles to give my constant C2, and in that case, the B cycle, the B period gives the constant C1. Right? So when I vary x, this differential depends, of course, on x, but the periods will stay constant. Okay, so what is good about this differential is that, okay, we put the poles of this differential at the Picard solution, right? Well, the Picard solution is the projection of those poles at the base. So the poles of this differential is at the Picard solution, and the differential will have two zeros, and the zeros will also be one above each other. They will be paired by the elliptic involution. They're here, and they will project to a point which I denote by y, and this y as a function of x is a solution to another Pan-Levy equation. This Pan-Levy equation with those coefficients. Right? So this differential has poles at the Picard solution and zeros at the solution to this Pan-Levy equation. Let's call it Hitchin's solution, because Hitchin was the first person to write the general solution to this Pan-Levy equation. Right? So this differential actually works as the Okamoto transformation. It transforms Picard solution to the solution of this equation, and it does exactly the Okamoto transformation. Right? And we can express the derivative of the Picard solution using this differential. The omega here is a holomorphic normalized differential. So of course we have to choose a marking of our elliptic curve. We have to choose the A and B cycles beforehand. Okay, so this is a nice differential with nice properties, and we want to generalize it. Okay, but before generalizing it, I want to show you another nice property. We can write a solution to a Schlesinger system using this differential, okay? Because the Penlever-6 equation is equivalent to the Schlesinger system with only one variable. And when we put Fuchsian singularities at 0, 1, x, and infinity, then we have only one Fuchsian singularity that varies, and our Schlesinger system in that case becomes just the Penlever equation. Well, doesn't become the Penlever equation, but is equivalent to the Penlever equation. And so this is a Fuchsian system with singularities 0, 1, x, and infinity. And then we know under some well, these are not assumptions. So if you look for traceless solution of the Schlesinger system and 2 by 2, we can get this by conjugation. This is the minus residue at infinity. Then for the matrix A, the 1, 2 entry is of this form. It follows from everything here. And it has only 1, 0, and it's 0. The 0 as function of x is a solution to this Penlever equation, right? So if we take our Penlever equation, and then the eigenvalues of the AJ have to be such, and we can directly write this A2, the A12 entry of the matrix, because we know something that vanishes at the solution of the Penlever equation. We can write immediately an expression that has only 1, 0, and that 0 is placed at the solution of this Penlever equation, right? Because we know this differential omega. This term is to kill the pole of omega. This is the Picard solution, and the rest just follows from here. We divide by a little omega to make it a function, and to make it a function on the base. Right. So this is the 1, 2 entry of the matrix, and then with a lot of work, we can derive the other entries of the matrix. But this is the starting point, and that's the main thing, right? So like this, we can have a solution to Schlesinger system with given eigenvalues, yeah, traceless solution and 2 by 2. So. And I just want to remind what we started with. We started with just a point in the Jacobian, an arbitrary point in the Jacobian, and then the assumption that under the variation of the curve, the C1 and C2 stay constant, right? We once got a comment that this solution is only halfway good because it uses the Picard solution. It's like because it's written in terms of another solution, in terms of something else. But this Picard solution is just, well, one point there that we map back by the Abel map. Yeah? We take the preimage by the Abel map, and we get the point Q0, and that's it. Okay, so we want to generalize this, right? And there is one straightforward way to generalize it to a hyperelliptic curve. So now I have a hyperelliptic curve with the ramification points projecting to all the Fuchsian singularities, which I still call the UJ. And I want to take a point in the Jacobian, again, an arbitrary point in the Jacobian, which will have this form. C1 and C2 are now constant vectors. And now I want to consider a family of such curves parameterized by the projections of their ramification points, right? So, and I'd like to again define this point Z0 on the varying Jacobian by requiring C1 and C2 to stay constant. Yeah, the B will depend on the curve. It'll depend on the UJ, but I want the C1 and C2 to stay constant. And then I want to map this point back to the curve from the Jacobian. But if I take a pre-image under the Abel map, I will not get 1 point anymore, right? So I cannot expect to always have 1 point for all the curves. Even if I start with 1 point, I map it by the Abel map to the Jacobian, but then when I move to other curves, when I vary the UJs, this point will split into G points. So I have to have G points on my curve if I want to map to Z0 to be the image of the Abel map. Okay, so in a generic situation, all these points will not coincide with ramification points, will not lie on top of each other, and we can have the QJ star, the hyperelliptic involution of those points, and we can generalize our omega in this way. So it's this is the same, and except that C2 is a vector because omega is now a vector of holomorphic normalized differentials. So I have to fix the A and B cycles for all the curves consistently. And so I'll fix so that the projections of A and B cycles on the U plane, on the base of the covering is fixed, is constant, does not vary from one curve to another. In other words, I allow only small variations of the U's. Right? So again, the periods of my omega stay constant. They are the same for all the curves in the family. And with this differential, I can play the same game and I can write a solution to the Schlesinger system. Well, it's here. The only, well, I don't want to go into details, but it's again written in terms of the omega. We produce the 1-2 entry and we reconstruct the others. It's again a solution with eigenvalues plus and minus 1,4. So phi here is this holomorphic differential, non-normalized. And then we have the Vj. Vj is another basis of holomorphic differentials normalized by these G conditions using the value of the leading coefficient and the expansion at the points of our divisor. Right. Yeah, the divisor that is mapped to the point Z0. Okay, but today I want to discuss this other way of generalizing, the wrong way, when we have only 1 point mapped to the point Z0 for all the curves. So we have a Z0 defined again by that condition with constant C1 and C2. And we assume that we have a family of curves for which the pre-image of by the Abel map of Z0 exists and exists as 1 point for all curves.
So G copy to one.
No,
The divisor is still degree G, but it's the same point.
no, not divisor of degree G, just like this. 1 point is mapped to Z0.
Yeah, but the inverse of the Abel map is a divisor of degree G. So it's the same point multiplied by G.
But I don't have the coefficient G here. I want this. No?
Okay, the point is identified, it's just that the divisor is still.
Well, you can consider Abel map on divisors of degree of positive divisors of degree 1, right? You can just map 1 point, just points, not divisors. The image will still be in the Jacobian, right?
No, it's not G times that one. It's just 1.
Yeah.
Multiplicity 1.
But the inverse of the Abel map.
Yeah, but maybe she's not taking the inverse of the Abel map.
Oh, you're not taking the inverse of the Abel?
Not in, well, not the inverse of the Abel map, that when you consider the Abel map going from divisors of degree G to the Jacobian. Can you consider the Abel map as just mapping points of my curve to the Jacobian? I can, right? I will not get all of the Jacobian. I don't claim that I will get all of the Jacobian, but I'll get something, right? And I can take inverse there if I'm lucky. And what I want here is a family of curves where I'll be lucky. I want a family of curves where I can have a section of that family, right? When I have a point on each curve, such that if I apply the Abel map to that point, I'll land here, where Z0 is that.
I guess what I don't understand is when you say a family of curves,
Yeah.
you talk about hyperelliptic curves, so you can think of it as Z squared as some polynomial in something,
Exactly.
and you're varying those things.
Right. I vary those something.
So what does it mean the same point? If these are different curves, so what's the same point?
Well, then I guess I have to talk about a section of a family, right? So I have a point on the curve is what? Is V and U.
Okay,
Right.
I think I understand. So I don't want to take up more time, but you really have a family of curves. I don't know how many parameters there are. A family of curves. Each one of them has a single, I mean, a map from the Abel map of the divisor, positive divisor could be 1. And you're saying they all land on the same point. And so
Same.
you're identifying those points, but in fact, those points are different curves.
Yes, yes. So that's what I want. I want a family of curves such that on each of them there is a point that maps to Z0, right? Z0 is not the same point also, right? Because this will be different for different curves. The Jacobian will be different, right? And the Abel map will be different. But I want them to land at Z0, which is written this way. Yeah? And the same way for all curves. The B is different, C1 and C2 are the same. So of course I have to choose the B cycles and the A cycles consistently for all the curves, so that the projections, the way to fix them is to fix the projection of A and B cycles on the base of the covering, right? So I allow small variations of the U's which do not perturb my fixed cycles, right? Okay, so I don't say we have to know that such a family exists, right? So a priori, not clear at all. And here is just everything I've said so far, basically, right? So suppose we have a family of curves such that, well, the first 3 points are easy to have. Yeah, they consisted of choice of homology cycles. That's easy to have. I'll just restrict the variation, how much I can vary my parameters. And then I have a point at infinity on all the curves, and that's where I will base my Abel maps on each curve. Then I have 2 constant vectors. That's also easy to have. And then, so that's the non-trivial condition. I want to have well, this is my parameter space. I want to have this section for each for each set of parameters. I want to have a point on my curve such that this holds. So this is a point at infinity on each curve. This is my point Q0, and I want it to land on the point Z0. Right? So if I have it, if I can have it, then I can define such a differential, which will generalize exactly this Okamoto differential, the differential that was doing the Okamoto transformation. So I will not have a sum here over all points in the divisor of degree G. I will just have this. And then we can hope to play the same game as before and to write a solution to the Schlesinger system. Okay. So now I'll try to convince you that such a thing exists. Such a family of curve does exist. Okay? So here is the classical thing, Chebyshev polynomials that we all know and love. What they do? They're defined on the interval -1, 1, and their values also oscillate between -1 and 1. Right? So this is T6, has 5 extrema. And all these polynomials, they satisfy the Pell equation. This is the Pell equation. And this is my Chebyshev polynomial. Here I have a polynomial that vanishes at the ends of the interval at -1 and 1. So this polynomial vanishes there where t is equal to plus or minus 1, right? For this to give 1. So this is the polynomial that vanishes at the extremal points. I've calculated this example. It works for T6. Okay, so if we divide out by the leading coefficient, we'll get a monic polynomial that is that satisfies this property of the minimal deviation from 0 on the interval -1 and 1. Right? Here is a quotation that Vladimir Dragovich found, but I like it very much. A quotation from Lebesgue. I assume I'm not the only one who does not understand the interest in and significance of these strange problems of maxima and minima studied by Chebyshev in memoirs, whose titles often begin with "on functions deviating least from 0." Could it be that one must have a Slavic soul to understand the great Russian scholar? Well, now we know that there is nothing about the Slavic soul. Yeah, everybody understands the significance of Chebyshev polynomials. Slavic soul is not required. And now we also have the generalizations of Chebyshev polynomials. Started by students of Chebyshev, Zolotaryov. And Zolotaryov studied polynomials deviating least from 0 on 2 intervals. And since then, there are many intervals, right? So instead of the interval -1, 1, we can have a collection of intervals and ask the question, what's the polynomial of degree n that deviates least from 0 on these intervals? And we don't care what it does outside of the intervals, but on these intervals, we want a polynomial that deviates the least among all polynomials of degree n.
In the sense that the distance squared is minimized?
No square, just absolute value.
Okay, absolutely.
Yeah, the uniform norm is minimal. Yeah, so it's maybe a little confusing because I show polynomials that oscillate between -1 and 1, but we get from those to those that deviate the least from 0 by dividing out the leading coefficient. I forgot the condition monic. Yeah, so we want to find a monic polynomial of degree n that deviates least from 0 among all the monic polynomials of degree n. Okay, but when it's not monic, it can be well, if you multiply by this deviation from 0, you get a polynomial that oscillates between -1 and 1 on the given intervals. And outside of the intervals, let's call them gaps. In the gaps, it goes out of the interval -1, 1. Well, there is one more condition when we look for a polynomial that deviates least from 0. There's a condition of monic of degree n, but also we have to fix how many times it oscillates on each interval, right? Because here, well, these two situations are different because this polynomial oscillates on the first interval more. And but when we fix the number of oscillation on each interval, it's called a signature. Yeah, so we fix the signature of the polynomial. So we look for a polynomial that is of degree n, that is monic, and it has the same signature. So we look at the class of such polynomials, and then we want the one that deviates the least from 0 in the sense of uniform norm. The pictures I stole from the paper of Dragovich and Milena Radnovich. Okay. Right. So every polynomial that does this, yeah, every polynomial that does this and for which the set of intervals is maximal. Yeah. So here, if I increase one of the interval, if I enlarge it, I will lose this condition that it is confined between -1 and 1. So when the intervals are maximum, in the sense that I cannot enlarge them, then the polynomial will satisfy the Pell equation, right? So the mu square here, it replaces this polynomial, right? And the mu square is a polynomial that vanishes at all the endpoints of the intervals. And of course, I call it mu square because we want the hyperelliptic curve. So that's a hyperelliptic curve corresponding to this Chebyshev polynomial. Okay. So, but we not only want a hyperelliptic curve, we want a family of hyperelliptic curve, right? So we want to vary the xj's there, which I used to call uj. But then we will have a problem because we cannot vary the xj's independently here. Because if I just give an arbitrary set of intervals, there is no guarantee that I'll have a polynomial that I will have a solution to the Pell equation. Actually, this Pell equation is understood as an equation on everything. Like everything is unknown here. The indices here give the degree of the polynomials. So Q is a polynomial of this degree, and then we have its square, so its degree is double that. So the Pell equation is understood like this. We have a solution to the Pell equation if we have Pn, mu, and Qn. And the mu includes the intervals. So the Pell equation has a solution if we can have the intervals and such a Pn and Qn minus G minus 1 that's satisfied. Yeah? So for an arbitrary set of intervals, the Pell equation, there's no guarantee that the Pell equation will have a solution. So we cannot arbitrarily modify our intervals. But fortunately, okay, I'll say it here. Fortunately, there is work by Beherstoffer and Schiffermeier, and John, pronounce it correctly. I think these are Hungarian names.
They're not Hungarian.
No?
No.
Okay.
No, they're
Okay.
really German.
I thought that since they published in Acta Mathematica Hungarica.
People in Hungary.
Okay. Okay. Well, good. So there is a result by Beherstoffer and Schiffermeier that allows us to vary independently one endpoint of each interval, each except the first one, which we fixed to 0, 1, just not to have the freedom of affine transformations.
But
So
Schlesinger was Hungarian. That's not a very Hungarian name.
Schlesinger was Hungarian. I didn't know.
Schlesinger doesn't sound very Hungarian.
No, okay. I thought he was German from the name.
Well, he didn't live in Hungary all the time, but he came actually from Pennsylvania, but from Hungarian part of it.
Good. Cool. Okay. So those theorems allow us to vary the one endpoint of each interval. So let's say we're going to vary the left point, the left extremity of each interval, and that the right endpoints will readjust accordingly to keep the Pell's equation satisfied in the same class of polynomials. So Pn will be still the degree n and with the same signature. Okay. So this way we can have independent half of our parameters, except these two will be independent points and the other half dependent points. That's how we come to this constraint variation. Okay, but now I'll go back a little bit and say why we want Chebyshev polynomials in the story. It's because every time we have a solution to the Pell equation, the corresponding hyperelliptic curve has a point of order n at infinity. So we'll have here a hyperelliptic curve that has 2 points at infinity. There is no ramification, right? Because we have pairs of points, the endpoints of the intervals. So here we'll have 2 points at infinity. And if we base our Abel map at this point, defined by this condition, then the Abel map of the other point will satisfy this condition. Yeah? So n times this will be 0 in the Jacobian, and that's what is called a point of order n. And this is what we want. We want curves that have a point of order n. Here is a proof of the fact that it has the curve has a point of order n, and it goes by noticing that the Pell equation gives this factorization of 1, and we can call this a function on our hyperelliptic curve. Let's call it function s. Yeah, so it's a function of x and mu is a point on the hyperelliptic curve. So this is a function of on the hyperelliptic curve. And if we consider the function of p star of the hyperelliptic convolution, we only need to switch the sign of mu, and we'll have this. So this function satisfies s of p star times s of p equals 1. So whenever s has a pole, s of p star has a 0. Right? And obviously S of P has a pole of order n at infinity. At this infinity, it will have a pole of order n. It's a polynomial of degree n in x at infinity. So then it has a pole of order n at this infinity, therefore it has a 0 of order n at this infinity, and by the Abel theorem, that amounts to exactly this. Right? Okay, that's what we want. Now, right. So now when we start varying the intervals, we'll have a family of hyperelliptic curves, right? And they will be parameterized by G parameters, which correspond to the left-hand points of our intervals. And the other G branch points will be dependent. Their values will be dependent on the axis. Right? And I have a point of order n at infinity. So now what we are going to do, we are going to apply Möbius transformation, which will map the last dependent point to infinity. So the infinity will become ramified, and the point from infinity will come to the finite place, and we denote it Q0. That's the image by the Möbius transformation of the point of order n that was at infinity. Then we have the UJs will denote the UJs, the image by this Möbius transformation of the dependent variables, and the XJ hat the Möbius images of the independent variables of the left-hand points, right? So now we have this family of curves where the axes are independent and U's are dependent. There is a ramification point at infinity, and we have the Q0 in the finite and the affine curve. Right? And now, since we had the integral from one infinity to the other times n equals 0 in the Jacobian, now we'll have the same property with Q0 star and Q0 here. This is the image of infinity minus, and this is image of infinity plus under the Möbius transformation, right? So the value of the integral should stay the same because it's just the change of variables in the integral, our Möbius transformation. So what we have now, if we base our Abel map at the branch point at infinity, at the ramification point at infinity, then we have a point of finite order. Now it's the order 2n at each right. So here my C1 and C2 are K1 over n and K2 over n. So they're rational. So So I have a family of curves, each of which has a point Q0 such that the Abel map of that point, omega here is the vector polymorphic differential. The Abel map of that point is a rational point on the Jacobian. And everything varies smoothly. So because this is a rational point, the C1 and C2 are rational, and the variation is continuous. So the C1 and C2 are constant. We cannot vary a rational vector continuously. So they will be constant. So we have that. We have what we wanted. We have a family of curves, each of which has a point that is mapped by the Abel map to the same place. Well, the same place in the Jacobian, the same position relative to the axis of the Jacobian, right? So we have that. Therefore, we can define such a differential, and we can do the same as we did in the genus 1 case when we had bijection between the curve and the Jacobian. So now we don't have a bijection, but we still can have one point. What we lost is the freedom of variation of all the branch points. Now we can vary only half of them. But we can do the same thing as in genus 1, and we can write, well, first we can write these equations for the dependent branch points in terms of the independent ones. I don't know if I can call it an equation, given that here it's pretty transcendental in use, but yeah, the VM are these differentials that are defined using the G conditions, using the G special points. These are the ramification points that are dependent and the Q0. Right. So VM is the basis of holomorphic differential defined by these G conditions. And then we can produce a solution similar to the genus 1 case, but different as well for the Schlesinger system, still with plus and minus 1/4 as eigenvalues. And this solution will be a solution to the constrained Schlesinger system. Well, it's similar, but it's a long way still. It took us 4 years to do the calculation. Well, I think that's all I wanted to say. Thank you very much.
Any questions?
Just a piece of history. You mentioned that this was done by students of Chebyshev. Was Achiezen a student of Chebyshev, or?
Yes, Achiezen.
That started looking at two intervals.
Yes, yes. Well, I think Zolotaryov who started looking at two intervals, but Achiezen worked on that as well, and I think Achiezen went further, right? I don't know if he was a student of Chebyshev, probably not. I don't know.
Just a small clarification. So your hyperbolic curve is G and G.
Yes.
But at some point you wrote another one which included the U's as ramification points
I don't change the genus. I just did a Möbius transformation on the same curve, right? I just put one.
Oh, yes, of course. You just but you added U minus U1, U minus U2, etc. Right?
Where is that?
You have the G minus 1 zeros in the polynomial on the right. We just had it there.
Here, yeah. Well, it's still genus G, right? I have 2G minus 1, 2G plus 1 points here. Yeah.
Okay. Oh.
It's just that I moved 1 point to infinity.
Okay. So when you say that you have a family of curves, the parameters of this family are the x's and u's?
Are the x's, and the u's are dependent.
Right.
I can only vary the axis.
Okay. This is just a shot in the dark, but is for this family of curves, there are some Picard-Fuchs equations that you vary the coefficients. The periods satisfy a linear. It's a linear, linear first order system. Does that? I mean, in the Picard solution, that plays an important role.
Yeah, but the Picard-Fuchs, I understand it in genus 1. You're talking about higher genus?
Any deformation can be some differential equation for the way I think of it, differential equations for the cycles.
Yes.
It can also be thought of as for the polynomial forms, but
Yes.
and very often, I mean, there's a very close relationship between that particular action and an isomonodromic equation. And the way I think of it is that the Picard solution is the statement that the open cycles with moving endpoints satisfy the same differential equation that as the closed cycles, and that gives you the Panavitsic solution. And what must be the same for this, of course, it's not Panavitsic.
Yes, maybe there is a constraint Picard-Fuchs, right?
Right. But this is really solutions, okay, constrained, that's fine. But it's constrained solution of the higher order Schlesinger system to like that's equivalent, to the Garnier.
Garnier, right. Right. So there is yes, there should be a constrained Garnier system. Yeah, but we didn't get to that yet. But there must be, because where is it? Here, when we have exactly there, when we have a solution to the Schlesinger system with the normal way of generalizing, then yes, the zeros of A12 are solution to the multidimensional Garnier system. I had it somewhere on the slide. I cannot find it now. Oh well, whatever. The U coordinates of this omega are solution to the multidimensional Garnier system. And the other part of the solution to that multidimensional Garnier system are somehow obtained from this part, I think. But yeah, in the constrained situation, there should be some constrained multidimensional Garnier. Yeah.
Hitchin's original solution, I think, came from restricting an ambient flat connection to a family with poles to a family of curves. And so you get that would be a way of getting isomonodromy deformations, in particular seeing these constraints. In other words, you've got a curve, you've got some K poles, and the intersections at two of the points are determining all the others with the intersections. So it's suggestive that maybe this could be thought of as some sort of restriction of an ambient, something on a K-dimensional manifold to a J-dimensional family of curves, but a flat connection. So it's automatically isomonodromic. Does that sound completely wacky?
No, that sounds very interesting, but I'm not thinking in this way, the flat connection and the deformation of flat connections. I would love if you explained it to me, maybe one day.
The Hitchin solution is a locomotor transform,
Yeah.
a sequence of locomotor transformations applied to the Picard system.
This one.
Well, just one.
This one.
Yeah.
And that transformation is done exactly by this. Well, if you write this differential in coordinates, you'll see the Okamoto transformation given this.
So you should be able to read off the Hitchin system from the Hitchin solution from the Picard solution.
Yes. Well, except that in the Okamoto transformation, you have explicitly y0 prime. And we don't have the expression for y0 prime, right? Because if you take the derivative of this, we don't have a nice way to write it. Therefore, that's why we cannot use the explicit transformation to produce Hitchin solution from the Picard solution. But given this, we can. Yeah, well, if you like this type of expression, then you can, and you can plug this in the Okamoto transformation and show that this does exactly the Okamoto transformation.
I forgot, I had another question.
Sure.
The last one. Do you know what are the eigenvalues of the residue matrix?
Plus minus one quarter,
They're
1/4.
all plus or minus.
Well, it's because it all comes from here. Right, it comes from here.
So
And-
use the plus and the x and the minus, or which ones are plus and the minus?
No, but the U's are not eigenvalues of the
No,
matrices.
no, but the residue that you use.
Yeah. The residues at the UI, they're all plus minus 1/4. They're all minus one here and plus one quarter there. Yeah. Because that's the case for this Penlevy, and then we just do the
So it's
same.
the generalization.
Yeah. If you want, yes. Yeah. Thank you.
Okay. No questions? Okay, well, thank you very much.